Okay, so welcome to then lecture 27 of Information Theory 2. And today, what are we doing today? Well, today we're going to have a little bit of, I think, what will be fun. It's often fun for me, and I hope it's fun for you. And we're going to be talking about primarily cohomology of complexity and algorithmic randomness. And we're actually, are we now more than halfway through the course? I think we're getting there. We've now had, this is our last lecture of the first column. And if columns are any indication of halfness, then we are indeed halfway through the course, which seems amazing because to me it still seems like we just started yesterday. So how can that be, that we're halfway through? But when we're on the quarter system, everything, the first lecture seems like it's halfway through. We have a new reading. Everyone should read chapter 14 in our book. This is a nice chapter, and I'm going to be drawing a lot from that chapter, and a little bit from other sources, but primarily from that chapter. So I haven't yet assigned homework 2. Office hours, again, one is going to be next Monday. Again, this is just a reminder of information about the final project, and also a reminder about this deadline, which we have now. It's not next Monday, but it's a week from Monday. Okay, so I do want everybody to continue to be reminded of this deadline so that hopefully you're reading your hundreds of thousands of abstracts. And I was very glad to hear on Monday that a number of you started already on your search, because that's, when you do read that many abstracts and you do a literature search, you really need to start early, so that's really good. Okay, so we're not going to do a review because, a normal review, because last time we talked about the alternating minimization problem, and usually I do a review because it kind of refreshes you for things that are needed for the current lecture. Today we're going to do a review, but our review is actually going to go all the way back to lecture 2 from last quarter. So then the next set of slides actually comes from lecture 2 and lecture 3 to refresh ourselves from. So, and I'm putting this in I'm not putting this in the review section because it's so old, it's maybe new, I don't know. Old is new. Old always becomes new again. But let's go through it. So remember this picture. So what we're going to do is start looking at relationships of information and complexity measures of things. Including random variables, but maybe other things as well. And this Venn diagram was one that sort of showed the relationship between the entropic, sort of the Shannon entropic quantities, where you have the area, any one of these areas. So you have, of course, it's 3 circles and they're intersected, and you have a number of different types of intersections. But you have the area, in some sense, corresponds not so much to the set of random variables, in fact, not at all necessarily to the set of random variables, but to sort of the common information. So area really means, in some sense, information. And so anything that's common, like if we take the intersection of, say, this circle and this circle, then this region here, which I will highlight in this color, is really the common information amongst both x2 and x1. Okay? So that's something to be reminded about, how we use these pictures. The second thing to be reminded about is to sort of go back to something that's very, very old at this point, and maybe we now at this point sort of assume is a given, which is our notion of information. So in lecture 1 we said, well, what are ways of measuring information? And we said that entropy was going to be the way that we measure information. So we have something which so far has been a collection of random variables, and we measure the information based on the entropy. And the entropy is based on, it's something that's useful, and it was derived from this Shannon's model of communication, and it corresponds to measuring an event as a probabilistic outcome. So this is an event that the random variable x equals lowercase x. That's an event, and it has a probability. And how surprised we are is basically equal to the log of the ratio. which is this right here. And then we said, this is actually a slide from lecture 1, 2, or 3, I can't remember, but basically we said, and this is something that we should all know now, that the entropy is the lower bound on the minimum number of guesses to guess the actual value of a random variable. Right? So this is something that we know because this sort of, it's the optimal number of questions to ask. So it says based on the probabilities, what's the outcome of a given random variable, and it will be equal to the average number of questions under the optimal guessing strategy. That's the entropy. It's also equal to the minimum number of bits to compress a source. And in some sense, you can think of it as like the optimal coding length. I mean, it is the optimal coding length. You don't have to think of it that way. It basically says that when you have a source, a random source that's governed by this distribution probability of x, that the entropy is the optimal coding length. And therefore, you can think of it as like the minimum description length. It's an MDL. MDL is a very common concept. It's the MDL of a random variable or random source. Again, without there being a probability of error. So we also asked the question back then, there's sort of the information about an event, which was basically the information of this event is equal to the log of the inverse probability. And this kind of makes sense because, if something's very, very improbable and it happens, what you find out should be much greater than if something is very probable and it happens. If something happens with probability 1, then you don't learn anything. If you watch a news channel and they always say the same thing and everything they're supposed to say is very predictable, how much information do you gain from said news channel? Right? And one of the things about the polarization of the news is that maybe when you have very polarized news sources, the actual information from news sources is very little because it's very predictable. So log, on the other hand, so when you have the log of a inverse probability, that's kind of right, because it basically says it's sort of monotonically related to the inverse of the probability. But why necessarily should it be log? We considered some other alternatives, like, for example, the inverse root of some sort. For example, like we could take the probability raised, 1 over the probability raised to the 1 over n. Sort of like an nth root. And that also has the same kind of behavior. It doesn't decay as rapidly as log, but it may seem reasonable. Another example, like we also talked about this, is like the number of prime factors in the seal of the inverse probability. As the probability gets smaller, it's going to have more and more prime factors, right? Presumably, but it's not going to grow very quickly. Log has a number of attractions, which we saw, and this was this Hinchin's theorem. So remember, this was sort of a nice result, which convinced ourselves that maybe log is something that's useful or is reasonable. So basically, just to remind everybody, we have a probability distribution P, and this is the entropy is just basically a measure on the set of probabilities. It's a discrete probability distribution. And now if we said, okay, well, what are some properties that we want of any measure of uncertainty of a collection of probabilities? And so let's say that this guy, script h of p, is some measure that has the following properties, the following 3 properties. Property number 1 is that it should take its largest value for the uniform distribution, number 1. Number 2, now this is an important idea. So like, how would you measure the conditional distribution? So this right here, this is basically just the same h, but it's measured on the probability distribution governed by p of y given x, for some particular x. So the idea here is that x is fixed. All these guys are the same x. And we're looking at the conditional distribution, p of y, given that x is equal to x. And so we can then compute this measure, script h, on that probability distribution, and then take the expected value of it, which is this whole thing. And that can be then just written as basically the expected value of this, where again this notation here just means what I said. Right? Now, does everybody understand this? I mean, this is basically saying, okay, well, whatever conditional distribution arises from conditioning on x, we take the corresponding row of that matrix and compute script h on that row, and then take the expected value of the resulting script h. So what we want then is that if we were to take the expected value and then we define the conditional information, this conditional information here, okay, then we must have the following property, so that if we have the information of two random variables, which is just a joint distribution over, maybe n squared probabilities, that's equal to the information in the first plus the conditional information of the second given the first, and vice versa. So that has to be a property. That's a property that we think seems natural, sort of an additivity property. And then the third property that we are asking for is that if we do have a probability distribution over n plus 1 symbols, where one of those symbols has probability 0, knowing that an n plus first symbol has probability 0 should not increase the uncertainty, or shouldn't increase the information. Right? So a zero probability event doesn't, according to this assumption, should never ever affect our measure of information or our measure of uncertainty. And that's this property down here. So anyway, what we said was that if these three properties are true, then the only measure that satisfies it is one that has the following form, or this form. And where lambda is some positive constant. And so basically this is just the entropy under some base of the logarithm. So entropy has some nice properties. But then on the other hand, is it the only one? And that's what we really want to talk about today. And so here's some instances of complexity. So this is where the fun begins. Okay, so let's consider this string. So this is, by the way, if anyone doesn't know, that when you have a 0, 1 with a bar over it, that means 0, 1 repeated infinitely. So this string is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on and so forth. So it's just repeated pairs of 0, 1s, and it goes on forever. So what do you think about this string? Is this a nice string? Is it something that you'd like to utilize? What if you had this string and you wanted to, say, compress it? So it's just a string, first of all. There's no probability distribution, it's just a string. How would you even bother compressing it? It's infinitely long, right? Is it compressible? Is it not compressible? How would you compress an infinitely long string? On the other hand, it's a very simple string to describe. It's conceivably very simple. In fact, I just described it there with only using a few symbols, and we can conceive of what that string is. And for all intents and purposes, I conveyed this string to you, which is infinitely long, without requiring an infinite description. My description, hopefully, wasn't infinitely long. I would be here for a very long time if I had to use an infinitely long description of that string. And in fact, one possible way of doing this, even in some sense on a computer, is just to have a program which says, print 0, 1 forever, or while 1, print 0, 1. That's essentially a description. And this print 0, 1 forever, in fact, is a 16-byte description of an infinitely long string. So I can describe this string without actually, giving it to you. And you have, for all intents and purposes, you have the string. Or alternatively, I could actually have, in some sense, maybe a 5-byte description of the string. Or maybe, easily I could fit that in 5 bytes, where I just have 0, 1, 0, 1 bar. See, which is even shorter. Okay, so somehow this string is very simple. I'm able to convey this string to you. And so while I'm not actually sending you the exact string, I'm sending you a description of the string. This is actually something that's very true about communication in general these days. Like, for example, when we communicate natural signals, like, for example, a telephone call through your smartphone, when you're listening to the voice on the other end, you're listening to the voice. It's actually not that voice. What is being sent to you? The way that the coding works these days is it's actually creating a description of that voice. It's not like, for example, sampling it and sending you a list of the samples. It's certainly not recording the analog waveform and scratching it onto a hardened piece of old dinosaur. What in fact it's doing is essentially coming up with a description of the signal and then sending that description to your cell phone, which is then reconstructing the signal based on that description and fooling you into thinking that that signal that you're hearing is really the one that was originally said, when in fact it's not. It's just a description. Another example of this kind of thing is like MIDI, musical instrument digital interface, where music is described not by, for example, recording a list, an actual analog waveform of the signal, but instead it's just recording note times and placements and velocities. And those are, so this is not really that new of an idea. In fact, this, what we're going to be talking about, isn't that new. But conceptually, these are things that maybe, you know, especially if you've done any communications theory or if you've done any digital music, maybe you're not that unfamiliar with this idea, descendant description. So here's another example. So here's a string. This is another infinite string. It's a binary string with a binary point after the first two digits. So it's 11.001000100011111111 and so on and so forth. Is this an easy string to describe?
Looks like pi, but you can't be sure.
Looks like pi, but you can't be sure.
3 point something less than 2 pi.
Yeah, it's hard to read binary point, isn't it? We're not sort of raised from, you know, junior high school to read binary point, but in fact it is a description of pi, right? So it's a description of pi, but it has no known periodicity. It has no known repeated pattern. It apparently, for all we know, it goes on forever without any pattern. It's a very complicated string in some sense. So is this something that is easy to describe?
Yes.
Why?
Why is it easy to describe?
Yes, this is a simple string from that perspective. So it's easy to describe. I mean, I could just say pi. It's easy to describe. Why? Well, the question is why.
Because we have all sorts of ways of reconstructing it from short.
Yes, exactly. So you either know this or have probably know the slides, but that's exactly. So the question is it easy or hard to describe? And it turns out that it's very easy to describe. The reason why is because we can describe it as essentially a ratio of two lengths, you know, based on a circle, or we can actually write a very short program. It's actually not. We can write a very short program. It's not a ratio of two lengths, but it's the you know what it is, right? Based on the circle. But the point is that we can easily write a very short program to produce pi to any degree length that we want. Okay, and the algorithm, the length of the algorithm isn't unbounded. The length of the algorithm is fixed. So rather than sending you pi, like if I could send you this very, very long, this infinitely long binary string, I could describe what pi is, right? Or I could give you a program and say, well, I'm not going to tell you the number of pi, but I'm going to allow you to, based on this program, generate it to your heart's desire. Right? So then what if we did this? Like, what if the algorithm itself is a code for the string? Like we have as our code book an algorithm, or I should say a code word is an algorithm. So rather than, what we do is we take the string and we map it to an algorithm which sort of indicates our code word, and then our code book consists of the set of algorithms for the strings that we were interested in describing. So in such case, what we would do, and this is again, in some sense, much more akin to the way voice communication works today, is we're sort of not really sending so much code words to represent a string, where the code words have some sort of nice sort of low-dimensional representation of the original signal, but instead what's really being sent is in some sense like an algorithm to reproduce the signal. So we could do that here with pi. So here's another string. This is a binary string generated based on fair coin flips. So we flip a coin, a fair coin, an infinite number of times. Is that an easy thing to describe? What if I send you a program that just says flip a fair coin an infinite number of times? Would that be short? It wouldn't work. And why would it not work? You get a different string with very, very high probability, right? So you want to send this particular string. So you generate this string based on flipping a coin an infinite number of times, and then you want to send that. You can't just send a fair coin and then do it again, because, like you said, you get a different string. So in some sense, this string is very, very hard to describe. Unlike pi, even though pi is very complex in certain ways, describing it in binary or decimal. Or this string is this fair coin flip string is very, very difficult to describe. The only way to describe it, the only way to send it to you, is to send you the string. And so the only program that would generate this string is to print the string itself. I could just say print the string. And so in some sense the program would have to have with it that particular string. So the program length in this case would be, the algorithm length would be infinite. So therefore this string is really incompressible, even from this perspective where we're sort of communicating by sending an algorithmic description of something. So let's consider then a string where we're not necessarily saying that there's a probability distribution over the symbols. We're not saying there's IID. We're not saying anything. But what we're doing is we're considering the complexity of a string, not based on the notion of entropy, but instead, because we don't have a distribution, but instead the complexity of the string is based on the length of an algorithm that can produce that string. So for the examples above, we'd have repeat print 01. That would be one string. That's a very short description. To print pi, we'd say print pi, which is the program to generate pi. That's longer, but it's still a relatively simple description. Right? It's short and finite length. The third program would be print B1, B2, B3, B4, and so on and so forth. So that would be a very, very long description length, because the string itself needs to be part of the program, and the string is infinitely long. So one thing you might say, and maybe you've had this question, is like, what do you mean by the algorithm? I mean, if I run this on Java, or if I run this in C++, or if I write this in assembler, or if I write this in Haskell, or if I write this in MATLAB, I mean, each one of these programming languages, I will have a different length, right? And so what do? Do I count the number of bytes of each one, and do I then take the... It turns out that we don't really care about what kind of computer we're using, or what kind of language we're using, as long as it's sort of Turing equivalent. And so what we're going to do is, first of all, talk about why it is that we don't care what language we use. Since if we had essentially a universal Turing complete computer, all computers can simulate each other with polynomial penalty. And polynomials in some sense don't matter. So what is a Turing machine? Well, the Turing machine is basically, it's an old, Alan Turing came up with the idea. It's an old idea from the 1950s, which at that point was based on the sort of dominant model of computation, but which was computers and tapes. But basically all computers, all reasonable computers, like other than quantum computers, are equivalent, or polynomially equivalent to a Turing machine. So what is a Turing machine? So a Turing machine basically consists of an input stream, where you have this, right? It's read sequentially. You have a working tape. You can have infinite memory, right? And then you have an output stream, which is here. Okay. And the idea is that you have a finite state machine, which sort of governs this bit here. This box is meant as a finite state machine. And so it's finite state, meaning that we can only sort of be in one of a finite number of states. And what is a finite state machine? It means that, I should also say that, so we have this tape, this infinite length tape, a read-write head, which can either read or write to the memory. So we can either read from this tape here or write to it. So we can read something, we can write something now and then read it again later, just to store stuff. And we have a finite number of states. And the basic function of the machine is based on this function delta. So you're in one of these finite states. So based on, you're in the current state, and then you read the next input, which is maybe this guy. You read the input from here, and based on the current state and the input, you can do one of three things. You can either read or write on the tape. You can write something to the output here, or you can move to a new state. Or maybe simultaneously you can do the same. Like you could read some work on the tape, and based on what was read from the tape, from the state, you might move to a different state. So it's a very simple machine. Okay. So it turns out that all standard models of computation, including MATLAB, Java, Python, C++, Flash, that's all there is in the world, right? Haskell, all of these languages essentially can be reduced to Turing machines. And this is based on, this is basically the famous Church thesis, which says that a Turing machine can compute any function computable by a reasonable model computation with only polynomial time additional cost. I should say polynomial cost, because polynomial time and memory cost, additional cost. So effectively, from the perspective of polynomial time reduction, which is what we care about as opposed to exponential time reduction, a Turing machine is equivalent to any other model computation we have, including all parallel computers as well. And as long as the number of processors is finite, right? So that's basically a polynomial time. So this does not include models of quantum computation, which we're not going to get into in this class. But there's been a lot of discussion, and both sort of actual and philosophical discussion about whether or not a quantum computer and quantum computation is practical and whether one can be built. But the kinds of things that happen there are pretty different. So we're going to make then the following assumption, that all computing devices that we have to deal with are equivalent to, in some sense, this universal computer U. Okay. So we can think of U as a universal computer, and then any differences we get in either description length or memory cost is only a polynomial function. And so, just notationally, just to get familiar with the notation that we're going to use, so U is going to be our computer, and this kind of funky font P. If you're interested in the actual LaTeX name, it's called MathFrak P, but let's just call it funky font P. So the funky font P is going to be a program which the universal computer can then take as input and run. Okay. Oh, one other thing we need. The length of this program is going to be L of P. So then, lastly, we can sort of think of this as saying that, well, we can run P on the universal computer U to produce some output. X is going to be the output. And for example, we might say, here's a string X. Find me a program P that when given to the universal computer U produces X. So all programs that do that will in some sense be seen as equivalent. So with that said, we now have the facility to define our sort of next main notion of complexity, which is really a form of algorithmic complexity, or it's also called the Kolmogorov complexity. The Kolmogorov complexity is defined in the following way. So it's a complexity of a string, number one. It doesn't require a probability distribution, and it's measured according to this universal computer U. Is defined as, so here's the argument X. It's basically saying, it's an optimization problem. It's basically finding the minimum length, so here's the length, program, such that, so it's minimizing over this feasible set. So it's all programs such that when the universal computer runs that program, it produces the string that we want. And then secondly, the program has to stop. Right? Like, for example, what can't happen is that it produces the string and then goes into an infinite loop. We don't want that. We can't have that. What it has to do is it has to produce a string and say, okay, I'm done, or it has to halt. It's called the halting programs. It has to end. It has to run exit if you're a C++ person. Exit 0, preferably. And if you're a Python person, I don't know what the equivalent exit is, but it has to do something. And it can't crash. That doesn't count. So therefore, the Kolmogorov complexity is the shortest algorithmic description length of a given string based on some program P that's run by some computer U. So what do you guys think? Is this a nice, do you like this way of measuring complexity? It's a description length. So like for example, let's say that X is me speaking on a cell phone. And so what this thing does is it says, okay, it searches over all the programs, all the infinite programs that basically can describe my voice and halt, and then it finds the shortest one, and then it transmits that over the internet. And then on the receiving side, what you do is you run that program and it regenerates me speaking. The program may look completely different than the original analog signal that was then compressed. And because after all, I mean, me speaking, there's no probability really in any given instance of an utterance. In fact, any signal you look at, when you measure it, probability, we're not even certain really that probabilities exist. Probabilities are sort of our model of uncertainty. It's our way of representing uncertainty. It's our way of acknowledging that there are things in the universe that we aren't aware of and that we don't know and we can't account for. And rather than essentially coming up with a ridiculously complicated set of differential equations to describe all of these idiosyncrasies of signals that we deal with every day, we instead said, we sort of punt. We give up and say, okay, let's just assume it's Gaussian because it looks Gaussian, not because it really is, or not because we really think that there's true randomness. It's just because there's all sorts of other interactions and craziness that's bouncing around in the universe that's creating what appears to be, and what, for all intents and purposes, might as well be considered noise. So this basically avoids all of that and says, why bother with that? Let's just sort of describe that signal that you're interested in algorithmically.
Okay.
Do you like it?
No.
But the penalty is that you need to like check all those algorithms that gives you that specific string, right? I mean, the description is unuseful at the end of the day, right?
The description is not useful?
You have to like go to that randomness, that like randomly actually modeling things.
Well, conceptually you don't, do you? I mean, conceptually, if you have a signal you want to send to New York, say, you just find a short algorithm and you send the algorithm. And then when they're done, they have an equivalent computer on their side. They run the computer and they get back the signal. All you've sent is the algorithm.
I mean, that algorithm was not like, you can't find that algorithm using this description, right? I mean,
Well, we need to talk about this. I mean, conceptually, what you could do is sort of diagonalize and sort of search for all. You could run a search process and just start from the shortest programs and get a little bit longer and a little bit longer and a little bit longer. At some point, if there is an algorithm that describes the string, at some point, and if there's a finite algorithm that halts, we're going to talk about the computability of this, and because the halting is a little bit tricky. We will get into the whole notion of the halting idea. But without actually dealing with the halting thing for the moment, suppose you had a procedure of detecting, like you ran through and you considered all halting programs, if that was possible, which we will talk about, but you ran through and considered all halting programs, and you saw, and you go from shortest to longest, and at some point you're going to hit the shortest one. And the first one you're going to hit, so the first halting program you hit that generates the string, you know is the shortest one because you've considered all shorter ones. And you don't know how long it'll run, but you will get it potentially. So conceptually, it's possible if you can detect the haltingness of a program, which we want to. I'm not sure we're going to get to that today, but we'll definitely talk about that on Monday. So basically, the definition requires that P does halt, meaning that it does terminate. It has to terminate at some point. Not all programs halt. And there's reasons for excluding them. One of the reasons is, for example, we want to run all short programs and see if it generates the thing. What if a program generates all but the last character of X and then spins forever? For some reason, it's a very complicated program. We won't know unless we run it forever. Do we wait 1 million years? Do we wait 100 billion years? And then after 100 billion years, it suddenly writes out the last character, or so we need to, or does it run forever? And so we can't. We have to somehow exclude those non-halting programs if we were interested in, for example, this quantity as a strategy for compression. So here's an example. So a natural number, let's say it's a non-negative integer k, can be written as the sum of n squares if it's possible for k to be written in this fashion. So basically, we have a set of bi non-negative integers. So all of the b's can be 0, 1, 2, 3, 4, and we're saying that k can be written as the sum of n squares if k can be written in this way. This will be part of an example, but I just want to make sure what it means, that you're clear about what it means to be, for a number k to be writable as the sum of n squares. This is what we mean, that there exist these b's. So basically, consider the problem of computing the smallest natural number that is not the sum of n squares. So remember, the b's can be 0. What's the smallest number that can't be written as the sum of n squares? And n is a parameter. So like, for example, if we wrote, the smallest number that can't be written as the sum of 0 squares is 1, right? Because 0 can be written, well, maybe 0 would be the right answer there. But basically, 0 can be written as no squares. But it's either 0 or 1, depending on whether or not you include 0 or 1 on it. But basically, 1 is is something that cannot be written with the sum of 0 squares. Right? I guess 0 can be written as the sum of 0 squares, because it's the sum of nothing is presumably nothing. So I think 1 is a better answer there. So 1 is probably okay. So what's the smallest number that can't be written as the sum of 1 squares? Well, 1 can be written as the sum of 1 squared, because 1 is equal to 1 squared. Whereas 2 can't be written as the sum of 1 squared, because the square root of 2 is not a natural number. So that's this one. So p1 is equal to 2. P of 2 is equal to 3. Why? Because 2 can be written as the sum of 2 squares, right? It can be 1 squared plus 1 squared is equal to 2. So 3 can't be written as the sum of 2 squares. What about 3? So 6 can be written as the sum of 3 squares, right? 1 squared plus 1 squared plus 2 squared. 7 can't be, but 8 can be written in this fashion. Right? So therefore 7 is the smallest number that can't be written. So I mean, you can imagine a program that sort of goes through and iteratively checks, starting with a small number. And at some point you run out of numbers, and every number you do, you sort of diagonalize and you search over all these possible numbers. The number of numbers if n is fixed, right? You can search over all numbers until at some point all further ones are going to be larger than the number that you care about, and you're done, right? But for all of these arguments, p will halt, right? What is p for? Anyone have an idea?
I remember this from number 3. It's Lagrange or somebody. Every natural number is the sum of 4 squares.
That's right, every natural number. So what will happen if you try to run this, p of 4? And you do this iterative algorithm. So you're running p of 4 using an iterative algorithm, which is trying all possibilities. It'll never finish. It won't halt. So this instance, and it is Lagrange. So basically, Lagrange showed that every number is the sum of 4 squares. And so if we were to give this to a Turing machine, if we give this program to a Turing machine, this thing would run forever. But you need sort of better. This is why computer-based search doesn't always solve all problems, because you run search trying to find a solution, but if this is the case, if this ends up being the theorem, you need smarts to prove this theorem. If you were to try to do a computer search to prove this, you would never finish. Right? So, but you would never know if you stop it after 100 billion years. Maybe if you ran it for 1 more second, it would finish. So that's the problem. So therefore, p does not halt when given force input. So we have to deal with this halting issue. We have to only consider programs that halt. So here's another example. So let's consider very long strings, like strings that maybe are of length 10 to the 15th. And by the way, I'm using length. Length, we defined length before as the length of a program, but we're also using it to measure the length of any string. Okay. So So let's do a couple of examples. So let's say if we take E, you know, the natural number E to 10 to the 15th bits, the question is this complex via the Kolmogorov complexity? But what is KU of E?
Not 10 to the 15th.
It's not going to be 10 to the 15th. It's going to be probably a lot smaller, right? This is a pretty easy thing to compute. We can just write a program that just spits out that many bits just by computing E to that level of accuracy. Are most strings of length 10 to the 15th complex or simple?
What's the definition of complex? Is polynomial?
By K.
So it has to be polynomial.
No, nothing about polynomials, meaning do most strings of length 10 to the 15th. So like we said, E is a long, E expanded out to 10 to the 15th is a long string, which you said is not complex, right? Because it has a short description length. So the question is, there are lots of strings of length 10 to the 15th, right? There's 2 to the 10 to the 15th such binary strings. So would your guess be that most strings are like E in the sense that they have a short program that generates them? Or are most strings not like E, meaning that they have only long programs generate them?
Should be sure that
Most programs.
most of them, most of the strings in the universe are like sort of random.
Yeah, but why is that? Why do you think they should be short?
Seems like you could do some kind of pigeonhole thing to show that there would be, that you can't fit you can't fit that information in the shorter programs.
Yeah, I mean it's fairly clearly how many short programs are there? Just combinatorially, short programs are short, right? Short programs mean that they're, let's say that we're measuring programs in bits. So a program of 20 bits, there's 2 to the 20th of them. At most, because a lot of those strings might not even be programs. So there's at most 2 to the 20 string programs of length 20. Yet when we're talking about strings of length 10 to the 15th, how can it be possible that all 10 to the 15th strings have short programs? Because there just aren't enough short programs to account for all of the number of different long strings. So what this means, I mean, there's an exponentially larger number of long strings than there are short programs, and so what it must mean is that most long strings are complex. Most strings are complex. Only a small number, tiny sliver of long strings have short description length. So this we will see. This is a really deep idea because this will be able to allow us to define, and we're not going to really do this until next lecture, but this little idea here, we will expand upon this idea, and we're going to allow ourselves to define the universal probability of the universe with this concept, without actually defining probability as a frequentist or as a Bayesian. I mean, we'll be able to say, well, the universe is inherently, simple. For this reason, as you will soon see, but soon meaning Monday. But I hope that this idea at first is, I wanted to introduce this here before we do a bunch of examples, to sort of plant the seed in your minds to think along these lines while we are going through these slightly more mundane examples of Kolmogorov complexity. So let's just go through and say what I just said. So most such long strings are complex. Why? Well, there can't be that many simple strings of a given length, just because simple strings, short strings, are short. So there just aren't that many of them. There's no more than the number of short programs. So there can't be that many short programs. So let's do another little intuition using the method of types. So remember this notation. I will remind you if you don't remember. P of n is the number of type classes with denominator n. And we said that there's at most a polynomial number of them, right? This is the number of type classes. Q of n is the probability of string x under distribution Q, which is equal to 2 to the negative n, and then we have the Kobloch-Leibler divergence of the type of string x between the type of string x and Q plus the entropy of the type. Remember, P of x is the type of string x. Remember that what is x? X is a string, we compute the histogram of that string. So a type is just a histogram of the string. Okay. So if P is a type, and then T of P is the type class, which are all of the strings that have the type, and let's not use this color, it just doesn't look good on blue. So so this is saying that the number of strings that have type P is equal to 2 to the n HP, where H is the entropy of the type P. And then lastly, the probability according to Q of the type class. Remember, there are this many of such type classes, but the probability of that type class is approximately equal to 2 to the n KL divergence. So the most probable type classes, of course, are the ones that are close. So let's say we take a string x and it has type px. We have, just using this first term, we have this many things. Okay. So just from the perspective of like using entropy to sort of give us intuition, entropy is in some sense a measure of complexity. But what this is saying is that more complex strings are such that there are an exponentially larger number of them than non-complex strings, because the number of strings with this type class has quantity 2 to the nh of that type class of that type. And so, for example, the uniform distribution, the number of strings where there's an equal number of zeros and ones, which are considered complex from the perspective of the type, are more numerous than there are strings that are all zeros or all ones. Right? So the number of strings that has all zeros is just there's only one of them. Right? It's a type class in and of itself. So I should say it's a type class that has only one member. So this seems to then corroborate in some intuitive way this stuff up here. Right? So I think this is a good time to take a break, because this is just entropy. We, in some sense, seemingly have stumbled upon a much more fundamental measure of complexity than entropy. Although maybe that's not going to be true, but maybe it is true. We'll see. But the point is, we can't make this more formal by resorting to entropy, because again, entropy requires a probability distribution. Kolmogorov complexity doesn't. So let's pause, take a short break, and then come back and do some examples. Okay, so what we're going to do is, before we get into some of the additional philosophical implications of what we just touched upon, we want to go through and define a number of additional concepts. The first is the conditional Kolmogorov complexity, or Kolmogorov complexity. I think the official way of pronouncing it is Kolmogorov complexity, and it's defined, or I should say the Russian way of defining it is, so it's basically defined for a string, and we've got some other additional string that is sort of input to the program, but it's not charged. We don't charge the length. So take a look at the difference of the optimization problem here. We get to use y as input. We get to use y as input to the universal computer. We still have the program P that gets to use y, but it still has to be the case that program P with input y has to produce x here. And then we take the length just of the program P without accounting for the length y. And again, critically, we only are interested in those P that halt. So that's the difference. So what is k of x given x?
K of x.
So what's k of x given x?
Oh yeah, it should be low. Because if you have x as an input, you don't have to generate it.
You don't have to charge it, right? So k of x given x, the shortest program that generates any string given itself. I could just read, write, read, write, read, write. So that's just going to be a constant. And it's not 0. I mean, you still need to have something that reads and writes, but it's just going to be a small constant. What about k of x given y, where y is IID and x is also IID, and we have that x is infinite of y. We need that. That's an important one. So what is that then? Yeah, it's already written. Sorry, forgot. All right, so it's k of x. The length conditional column Markov calling. So this is different than conditioning on a string y. We're just conditioning on the length of itself. So this definition says that the program gets to use the length of the string x, but it doesn't get to use x itself. So it knows how long it is, but it doesn't actually have the string. And again, it's the length of the program that gets some additional information, but it doesn't get all of it. So do you think this increases or decreases the complexity? I mean, if this was entropy, we're sort of conditioned now to think that all things conditional help, right? What do you think? I'm not going to give you the answer now, anyway. I'm not going to give you the answer. So let's talk about this in a little while. I think you should think about it. This is again another one of these seeds that I want to sort of plant in everybody's minds. These are educational, pedagogic vehicles through which everybody learns more efficiently, right? Because what I do is I sort of plant things. This is a well-strategized lecture as opposed to something whereby you only find out questions when you're ready to answer them. So the notion of universality is important. So if you've got a universal computer U and another computer, say A, then basically they're all in some sense reducible or boundable with respect to each other with this additional constant, which is dependent on the computer A. And does anyone have, so basically the idea, I mean, it's almost too simple to actually have a formal proof, but what we do is we have some program that simulates A by U. So S of A is a program for U that can simulate A. So any program for A can be run by, thanks to the sort of church thesis, any program meant for A, which is right there, there's one of them, can be run by U. Oops, gotta get this better at this. Can be run by U thanks to S of A. And that basically gives us the same output as what A would do if it had P of A directly. So another way of saying this would be, for example, that given some P of A, which is a program for A, if we run P of A, if A runs P of A, and then if U runs S of A PA, we get the same output, X. Okay. On the other hand, I mean, this is just a concatenation, right? So if we take a program and an additional input to that program, the length is just equal to the sum of the program plus the sum of the additional input. And so the lengths are additive. All right, this is length. There's nothing fancy about the length function. Right? And so then we can just sort of rename this guy to be C of A. Right. And that, by the way, will happen to be equal to this C of A. So the other thing to note is that the K of X under U is going to be less than the length of SAPA. Right? Why is that? Well, K of X over U is going to be the shortest. It's going to be the shortest program that generates X, right? And SAPA is a program that generates S, and its length is, you know, that's going to be one of the programs that K of X is going to consider, and KU of X is the shortest one, and that's true for all PA such that A of PA generate X, because SA simulates. Remember, SA is a generic simulator. And so therefore, once we've got that, and the critical point here to realize is that this is for all P. So that means that this lower bound is also true for the minimum of the right-hand side. So it's the minimum where the right-hand side is right here. Right. So since it's true for the minimum of the right-hand side, we've got that the Kolmogorov complexity U of X, which is defined to be this one, is less than or equal to the minimum of the right-hand side, which is right here. And now all I'm doing is I'm just using this guy, the additive property there. But then CA is now a constant in this minimization, so we've got the result that we want, which is the right-hand side here. Yep.
So does this mean that like U is the optimal machine for P?
No, we're not saying anything about U or A being optimal. We're saying that U and A are any two universal machines, and S of A is a program that simulates A for U. It's kind of like saying, let's say that U is C++ and A is Python. And I've got a simulator in C++ that will run any Python program, right? That's all I'm saying.
It seems like you haven't qualified any relationship between U and A here. I mean, what if A is C++ and U is Python? I mean,
But that's true. You'd have a different constant. The only thing that's different is you have a different constant.
Can the constant be positive or negative?
No, the constant is always going to be positive. Why?
Yeah,
Because the length. Remember, because the constant. Remember what the constant is. Constant has to be positive because why? Well, it's equal to the length.
Oh, right.
Lengths are not negative.
Yeah.
It's
So
not going to be 0 unless A and U are the same.
So there's no time under which like A will be able to run the program like more efficiently or represent that program with less instructions than U.
Well, remember, S of A is a program that simulates any program for A by U. Right. So PA is a program for A. So if you just gave PA directly to U, it would crash or burn, or it's kind of like trying to compile Python with C++. Wouldn't work. Whereas if we feed Python to a C++ program that reads in Python run in C++, then we have to charge the cost of that Python simulator. And so CA is the Python simulator length. It's like the number of lines of code ignoring comments. And other people who put like semicolons and single lines and things like that. You know, I mean, some measure of length. There's a number of reasonable length of that program. So, but clearly, I mean, therefore, there's going to be this additive relationship on the length. So this holds. But yeah, no, you can switch these around. There's nothing special about U and A. It's just to get a different constant. It's just that the point is that every program, according to every program, it's bounded by another program based on some constant. Once the constant's there, the bound is true. So therefore, I mean, because everything's sort of constantly related to each other, or additively, it's constant, we can just ignore which computer it is, and we just say it's U. So first of all, conditioning. We do have a bound on the conditional homomorphic complexity, which says that given its length, k of x given L is no greater than the length plus some constant. So why is that? Well, the computer knows length, L, right? And this is, on the one hand you might think, wow, it's great, I've got a bound, which is really simple. On the other hand, maybe it's not a great bound. So you know that the computer knows the length, right? It has access to that. So one possible program would be print this sequence. It's a really dumb program, but it's a reasonable program that just says print it. And since it knows the length, that sequence doesn't need to be any longer than that length, right? Because this sequence itself has that length. And so, therefore, this program has length L of x plus c. And so, therefore, and anything else could only, we've now found a program, and k of x given L is going to be the minimum of all such programs with knowing the length that prints x. And so this, therefore, is an upper bound. Not necessarily a good one. There's no bits needed to store L of x. Why? Because that's part of the input. It's given. Okay, so like I said, this is not necessarily a good upper bound, but it's a bound, nonetheless. Here's another bound, relating the conditional versus the unconditional complexity. So basically, k of x is less than or equal to k of x given L plus 2 log L plus c. So let's think about the worst case. So in the worst of cases, k of x needs a way of representing, these are upper bounds, so we have to consider the worst case, for these really, really bad examples. The cases where k of x is really small, we just need to account for all of the cases, so therefore we need to account for the worst case. And so in the worst case, we need to have a representation both of the string that needs to be printed and also the length, right? So we can, once we know the length, if we know the length of the string, then we can use a program that's of length k of x given L to generate x, right? But now all we have left over, because k of x doesn't get to use the length, we need to store the length somewhere as well. So how do we store the length? Well, to store the length, we need log n bits, right? Where n is the length of the string. But the problem is we don't know how many bits to store the number log n, because we don't know what n is. So we need maybe more bits to store than just log n. And so one way to do this is to use 2 times the seal of log n bits. So the idea is that each bit gets duplicated. So when we want to represent a binary number, we represent 1 1 0 0 1 1 1 1 0 0 1 1, where each 2 bits, which are always the same, corresponds to 1. And then we have a special end code, which is say 0 1. And once we get to a 0 1, we say, okay, that's the end. And that at most requires 2 seal log n bits. So that's a nice representation. Maybe it's worse twice. Here's an example. So this number 5, if you wanted to store this 5, we would store it this way: 1 1 0 0 1 1 0 1. So this last guy here, this is the special end code. So this corresponds to 1, this corresponds to 0, this corresponds to 1. This is end. So we get 5. So therefore we get this upper bound, 2 log L. So therefore we get this whole bound. So it's very simple. I mean, in some sense, it's trivially simple. But again, these aren't necessarily very good upper bounds. But in the worst case, maybe they're actually not so bad. Because in the incompressible case, maybe it's a tight bound, because maybe you can't do any better than that. If you take the uniformly at random coin flips, fair coin flips, all we can do is store it. And so we can basically say, well, here's this string. We need to say, well, here's the string and how long it is. And we need to store the length, and so this can do it. So maybe it's a tight bound even. It's not a bad upper bound, after all, for these very, very incompressible strings. But it's a very bad bound, obviously, for these other strings. But on the other hand, we just argue that there aren't that many simple strings. So maybe this is most of the time a very good bound. Here's another slightly tighter bound, however, because the way in which we're representing log n is not so good. We're representing it as 2 log n. But here's another way of doing it, where let's just call this log star of L, where log star of n is basically equal to log n plus log log n plus log 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 n plus and so on and so forth. And you keep doing that until essentially you hit 0. Okay, so how would we do that? Well, it's just another way of encoding the number. The first part is exactly the same. So this part here is the same. What we're going to talk about is really just where does this come from. And so we need log n bits to store n, right? So we can we need to store the number n, right? So we use log n bits. So we allocate log n bits, but we need to know how many bits we've used to store log n bits. So we can, right? So how do we do that? Well, we can store a number up to log n bits in log n bits, which is this. And then we need to know how many bits to allocate for log n, and that's log n, and so on and so forth. And we keep doing that until we hit 0, which will eventually happen. So therefore, we get log star n. Is it worth it? I don't know. Maybe. Okay, so there's complexity. Like I said before, there are many more, in fact, exponentially more long programs than there are short programs. We discussed this why, because there aren't that many short programs, because short programs themselves don't take that many bits by the fact that they're very short, and so therefore there just are not enough of them. So most strings are complex, which we want to start to formalize. Most strings are really complex, meaning that they have long description lengths. So here's an interesting way of describing that exactly. So the number of strings x where the Kolmogorov complexity is less than k is given by this formula. So this is the number of strings. This is just the count of the set of strings that have Kolmogorov complexity less than k is less than or equal to 2 to the k. So notice that this is 2 to the k, where k is the bound on the complexity. It's not the length of the string. So you could, so the number of, x could be very, very long. And there's way, way more than 2 to the k long strings, because n might be vastly longer than k. That's the length of strings that we might want to compress. But there just aren't. There's just not enough. I mean, of all of the strings that have complexity less than k, there's at most 2 to the k to them, and that's basically the proof. I mean, that's already the proof. I mean, intuitively. But let's just go through it a little bit more formally. So how many programs are there with length less than or equal to k? Well, there's 2 to the k of them, right? There's 1 program with length 0. There's 2 programs with length 1. There's 4 programs with length 2. 8 programs with length 3, and so on and so forth. In general, there's 2 to the k programs with length k. Right? Right? I'm getting a feeling that folks are beginning to not follow. I hope this is clear. 2 to the k programs with length k. And so if we sum up all programs with length up to and including k, we're going to get 2 to the k minus 1, which is upper bounded by 2 to the k. Okay. So each program, at best, there are lots of these strings that are just not even programs at all, but each program at best outputs a unique string x. Right. And there are at most 2 to the k such programs with complexity less than or equal to k. So that's it. So that's a way of formalizing it. There just aren't that many. So if you consider all of the possible strings of length n, where n is much bigger than k, obviously there can't be more than 2 to the k to them, and 2 to the k over 2 to the n is 2 to the what? K minus n. So the tiny fraction of them tiny exponentially small fraction of them, as n gets bigger, are going to have low complexity. That's actually another theorem we'll say in a minute. So if we were, for example, to look at all programs up to length k, like here's what we were talking a little bit about earlier. Like we could consider all programs up to length k, all 2 to the k of them, and maybe that's an exponentially growing in k, but maybe that's something that we could do in a few days or a week or something if k is not too big. And we don't find one such that u of p is equal to x, and we somehow have a way of detecting whether a program is halting or not, then that's basically saying that the complexity, we have a lower bound on the complexity of the string x. So anytime we haven't found one, we've searched all of them at that length and we haven't found one that generates it, that lower bounds the complexity. So it does have computational cost. If we could do this in the first place, it has computational cost exponential. But if you wanted to, if k was fixed, like if I only cared about whether or not the complexity was greater than k or not, the k was fixed, then this may be feasible. But on the other hand, there's going to be other complications, again, with regard to the halting issue, which we are soon to discuss. Here's another example, or a bunch of examples. What's the complexity of this? So the complexity of the string with n zeros given n. This is a question and answer session time. Hopefully you can come up with these answers very quickly.
It's just a constant.
This is just a constant. What about this? It's a n-bit expansion of pi.
Also a constant.
It's also a constant. What about this string? It's also a constant. What about, actually here's another one. Here's a binary string. Let's say it's an indicator of rain on a given number of days. So like each bit is whether it's raining, whether it rained that day or whether it didn't rain that day. Okay. And we want to compress this string, and then in fact let's use a Markov chain, right? So let's model as a Markov chain and construct this conditional histogram p of xi given x of I minus 1. And so that's four numbers, right? I mean, it's really only 2 numbers, but let's just say it's 4 numbers. And what we could do is compute this based on that string. We could count these pairs, like how many times 0, 0, 0, 1, 1, 0, 1, 1 occurs as counts. And the numerator of each of these histograms is at most n, right? Because there's only n days in the strings of length n. So for each one of these 4 numbers, we need log n bits. So therefore, we need O of log n bits to store this conditional distribution. And additionally, if we want to do like entropy compression, for each symbol, we could do entropy compression and use this many bits, the log of the inverse probability, to describe x in the context of x minus 1. Right? We learned this when we talked about arithmetic coding or stochastic processes, entropy of stochastic process. Right? This doesn't necessarily mean that this is really a first-order Markov chain, but we're using a Markov chain as a model of this string in order to come up with a description of the string, a short description of it. Even though the string doesn't have any probabilities, per se. We're just constructing probabilities by counting. So the Kolmogorov complexity then is equal to, given n, is equal to h times n plus O of log n. And I just realized that I think, if it's truly a first order Markov chain, then this is true. But in actuality, or in reality, I should say, this is an upper bound here. And why? Well, because hn bits are needed for the string itself, and then we need log n bits, order log n bits for the table, for storing that, because we need to store those probabilities. And then we've got a constant here. If, on the other hand, we add additional information like Seattle, then it becomes a constant. Why? Actually, I can't really say that on today, can I? It's less joke. I mean, when I first did this joke, actually, we had a run on rainy days for like I think it was like a succession of 486 days of rain or something like that, and so this was a very funny joke. So this joke doesn't really work now, but on the other hand, this is often very accurate, right? This is a very short program, constant length, that would be able to easily compress a string given that it's from Seattle. But anyway, not funny anymore, sorry. It's global warming, right? It's going to turn Seattle into Los Angeles into Acapulco, Acapulco into Venus. That's what's going to happen. All right, here's another interesting example. Fractal images. So let's say that we have a 2D grid. Are you familiar with like the Mandelbrot set? Is anyone familiar with that? So basically you have a two-dimensional grid, right? 2D image, and C is a point which has coordinates, which are, it's C real and C imaginary. So C it's a complex number. CR plus J, and we write J because we're in the electrical engineering department. CR plus J times CI. Right. And for each one of these points in this 2D grid, we have a different complex number. Okay. So then what we do is for each one of these points, we just literally run this program. We just initialize it. We initialize Zn to say 0, Z0 to be 0, and then we keep running this iteration. We construct Zn plus 1 for each C individually, independently, in parallel. Or it doesn't have to be in parallel, but just has to be done independently, separately for each one. So each point has no relation to the other point, other than the fact that the C's lie in this grid. The complex numbers lie in this grid. So we run this. until, well, I should say, I'm not being very clear here. So we run this thing where we just update z this way. And we keep doing this until this is greater than some tau, right? So, and we keep doing this until we get equality, which is this. And then we find how many iterations that took. Let's say it's n iterations. And then n indexes into some color map. Like if it's 76, then we use red. And if it's 79, we use blue. And if it's 168, we use green. We find some color map and we index into this color map. And then that becomes the color of that pixel. So what we end up getting is amazing pictures like this. I mean, that particular algorithm produces this image, this Mandelbrot set, which you've seen many, many times. So even though it's the case that we've run each pixel independently, we get these amazing patterns of self-similarity, and we can sort of do finer and finer granularities of the image, and we can zoom in on more of them, and go in on that part, we'll see the same shape. And there are many other fractally generated images, like for example this one is also fractally generated. It basically looks like it could easily be a landscape, a natural landscape, either on Earth or on Mars, or probably many, many places in the universe have things that look like this. It's a very common thing in the universe. Here's some, if we look at the Kolmogorov complexity of this, it's a constant, right? So the program is just this simple little program that doesn't require a lot, and it generates these very, very complicated images. So when you think about our entire world, our universe, the universe that we look at actual images, maybe slightly more complicated images or complicated programs could generate any scene that we may see. Like for example, clouds. Anyone know where this is? I think this is in Canada, isn't it? This looks like out our window today. Actually, most of these are probably from the Pacific Northwest, aren't they? But in any event, you can get trees or all sorts of things, maybe from a very simple program. And so it says something about or even this scene right now. I'm looking at a classroom packed full with students. Maybe that scene is easily described from a short program. Whereas random dots, random bits, random bit patterns, static on a television screen is not something that's easily described. So, but our natural world maybe could be easily described with short programs. Potentially. So think about that, hold that thought also, because that's something we'll discuss on Monday's lecture. Monday's lecture will be really deeply philosophical, by the way. At least it will involve some philosophy. So come with your philosophical chops. What about this? So a given integer itself has complexity no greater than log star n plus a constant. And again, why? Well, because we can store n in log n bits, but then we need to know how many bits we use to store the number of bits that we use to store n, so we need to use log n bits, and so on and so forth. So this is a simple little upper bound on the complexity of any integer. Kolmogorov complexity of any integer. Okay, let's do some more examples. Here's an interesting one. Let's say we want to construct a bound on the complexity of any binary string that has k ones and n minus k zeros. So how do we do this? Okay, let's sort, for example, consider all of the strings of length n that have k ones and sort them in lexicographic order. Right? There's a finite number of them, obviously, right? There's at most 2 to the n of them, but there's usually going to be many fewer of them than that. And then given any index I, we can actually write a program that has constant length, just basically consider the ith one and print out the ith one in that ordered list. Like the program could be something that generates, it's a short program that generates all possible strings in lexicographic order. It could be a really, really dumb program which generates all of them and counts how many ones there are, and if it is, then you increment the counter, and if you don't increment the counter, and whenever the counter is equal to I, you just go ahead and print it. It's a very simple program. It's not a very fast program, but it's short. Right? So therefore, to write a program to generate such strings, we only need to generate both k and I. Because we need to know, the program needs to know what is k, because it needs to know how many ones there must be in the strings that we're interested in printing out, and also needs to know which of those strings that have k1s in lexicographic order is the ith one. So for k, we need 2 log k bits. And this is used like very simple upper bound rather than log star k. In fact, in this case, we can even use log n bits. We don't even need to use 2 log k bits. Why is that? You will see. For I, I is an index that lies between 1 and n choose k, because that's the number of possible strings of length n that have exactly k1s. So I ranges between there, and so therefore we need log of n over k bits, log of n choose k bits. So why do you think we don't need a 2? Or this log star thing? Well, if it's not clear, we have n as the input, right? And k, so we already know the number of bits. We already have a bound on the number of bits we need to represent I, right? Because we can compute n choose k. And so we don't actually need to do that trick because we've got the length, everything that we need. Okay. So therefore, the length of this particular program is going to be some constant that's, associated with some fix-up stuff. We've got 2 log k plus log of n choose k. But then log of n choose k is equal to, well, it's upper bounded by n times h of k over n. Remember that combinatorial bound on the choose function that we use? So now we're suddenly using entropy of the ratio as our upper bound on the length. This was the original bound. Remember this thing? These are useful bounds, actually. Sorry, say again?
Entropy of k over n?
Yeah, so remember, k over n is think of it as a probability. So it's just the binary entropy of a probability with value k over n. This was something that we saw last quarter. So therefore, we have an upper bound of the following. For this program. So interestingly, entropy has come into play for our algorithmic compression. So we can still use entropic quantities. In this particular case, we used entropy only from the perspective of bounding a combinatorial quantity, which is namely, how many bits do we need for I? And the other thing to note is that if k is really equal to n over 2, say, then if it's got a lot of ones, then this is as long as the string itself. So if half of the string, because that's the maximum entropy, right? So that's 0.5, and then entropy is going to be equal to 1, and the bound is going to be 1. So this algorithm is not going to be very efficient because it's going to have to have a length equal to n, just to store the index. So. Okay. So we're starting to see then, we have these two seemingly very, very different notions of complexity. We have entropy, which we've seen for a while, and we have Kolmogorov complexity. Entropy requires a probability distribution over a random source. Kolmogorov complexity doesn't. It basically says that the complexity of a string we've begun to see in one or two instances that entropy can be useful to come up with Kolmogorov complexity bounds. But what we want to do is try to compare them a little bit more formally. And what we're going to see, in fact, is that they're very related. Although what we will need to do in all of these cases, and this is something that's easy sometimes to forget, is that when we're talking about these relationships, most of the time we're really going to be talking about the expected value of the Kolmogorov complexity. Okay, because we have to do something with this distribution. Entropy needs a distribution. Kolmogorov complexity only needs one string. So that's first of all one sort of normalization between the two that we're going to need to do. So let's, in fact, that's that first point. So the other thing I wanted to mention, we haven't talked yet about Lempel-Ziv compression. So it's also algorithmic, but it also converges to the entropy. That's another instance where we're going to see an algorithm that doesn't actually use probabilities directly being something that ends up converging to the entropy, which does use probabilities, which will be an interesting relationship. But first, let's look at this important theorem. This is important in a number of ways because, first of all, it's basically saying for all computers U, under any reasonable computing device, this number, so summing over all programs that halt of 2 to the negative length of that program, that's going to be upper bounded by 1 and lower bounded by 0. First of all, the lower bound of 0 is trivial because we're only summing positive quantities. The upper bound of 1, does anyone realize immediately why that follows? Let's try to zoom in a little bit. Does that look familiar to anybody? Think last quarter. Crafts inequality, there you go. So why does Crafts inequality apply? Well, it turns out that if P halts, then it can't be a prefix of any other program. Right? So any program that runs and halts is sort of done. That's not a prefix of some other program, because any other program which had that first program as a prefix would have stopped, and that additional stuff wouldn't have done anything. It would be the same program. So any programs that halt can't be prefixes of each other, and so therefore we've got a bunch of these strings which aren't prefixes of each other, and then by Crafts inequality, which only required them to be prefix free. This is the countably infinite Crafts inequality, by the way. This satisfies this. Secondly, what we're going to do is define this number omega. So omega, this is a number that lies between 0 and 1, and we're going to define this number omega. So this number omega is the magical number that I've been warning you about for 15 weeks. Right? This is the number that if you do this number, you would be able to answer any question in the universe. It turns out, as we will see, first of all, we're not going to talk about this until next lecture, but we're going to see why omega answers any question in the universe. How do you solve world hunger? It's right there in that number. Is P is equal to NP? It's right in that number. What's the name of the person I'm going to marry? I don't know, some of you might be married already. That would be an easy question. Omega knows the answer. Ask a question. What's any question? It's an oracle. It's an oracle number.
Can you add that as a primitive in your programming language?
Omega?
Yeah. And then
it will know the answer to whether or not you can add that as a primitive to your programming language. Just yes. It knows the answer to that question too. I don't know. I know that's a joke, but basically, we will see why this number is interesting. But I guess to not get your hopes up over the weekend, because I'm sure you will ponder and reflect and ruminate over omega until Monday. It turns out that omega can be shown provably to be unknowable. unfortunately, even though we know it exists. There's also, but we can study properties of it, as you'll see. We'll study some interesting properties of it. But before we do that, let's look at this next theorem. We're gonna do a couple more theorems before we get to this amazing magical number. X is drawn IID. So it's a sequence of random variables drawn IID according to some distribution P. And then create the joint distribution this way. It's just a product distribution. Then what this says is that there is in fact a relationship between the entropy of X and the Kolmogorov complexity via the following thing. First of all, we're taking the expected Kolmogorov complexity, right? So it's basically, it's the length of this, it's the description length of the string x of 1 through n weighted by its probability divided by 1 over n. So it's kind of like an expected per symbol description length, just like the entropy is, right? Because the entropy is like the per symbol number of bits you need to use. It doesn't say necessarily that you can code per symbol. We talked before that we need to do block coding. And this also says you might be allowed to do block coding because you could potentially just have one program to print out a given string. Right? We don't have to code each symbol individually. But the point is we have that this expected complexity is lower bounded by the entropy. So we haven't, somehow you might think, oh, this Kolmogorov complexity, does that help us violate the entropy lower bound? Shannon's entropy lower bound? What this is saying here is no, it doesn't. It doesn't help us compress any better than the entropy, for those cases that we do have a random number. It might be, this might be a very good code word length to use for X. And in fact, it is a very good code word length to use because we also have the upper bound, which says that, let's just look at this upper bound. Well, first of all, we have the entropy, which is just sitting there. And then we have these other quantities, which are going to 0 as n gets big. So as the block length gets big, it turns out that the Kolmogorov complexity becomes the ideal code word length. And since we know that it's corresponds to halting programs, the lengths of these code words satisfy craft, and so therefore there's a code that can be constructed that has the lengths equal to the Kolmogorov complexity. And the other thing is that this expected, I don't know why I put the n inside of there, but basically the expected value of this random variable, of the Kolmogorov complexity of the random string, goes to the entropy. Again, we're doing the 1 over n because it's the per symbol expected value. So what this is saying is that the Kolmogorov complexity is on average, as n gets big, no better, but also no worse than the code word lengths expressed by 1 over log of 1 over p. No better, no worse. Everybody see that? Okay, it's the statement of the theorem. This theorem we're going to prove. So let's consider error-free programming, or so error-free coding. Hopefully there's error-free. Actually, we do have error-free coding. We don't have error-free programming, unfortunately. So we're coding with these lengths, L of x of 1 through n. And we certainly know that the entropy is a lower bound of this. Right? This we proved before. Any lengths are going to be such that the expected length is going to be lower bounded by the entropy. And then let's code with the program. So the program is going to be our code word for each string. And therefore it satisfies craft. And I guess we sort of already talked about this. So it satisfies craft, and therefore we have this lower bound. Okay? So those lengths aren't particularly good. To get the upper bound, what we're going to do is we're going to encode for each string, we're going to encode the type of the string, and we're going to then again use this lexicographic idea of saying, okay, well, what's the type of the string And then secondly, what's the index within that sequence of strings that have that type? And then that's how we're going to do decoding. And we're going to achieve the upper bound. So we've got a string, a length string, and here's its type. So remember, a type is a histogram. And here's the histogram. It's the number of times, it's a sequence of numbers of length equal to the alphabet size, where the numbers are equal to the number of times each symbol occurs normalized by the total length of the string. It's the type. And so for each type, we need log n bits to describe each numerator, and therefore the alphabet times log n bits to describe the type. And then we enumerate the elements within each type class, and we also have this bound on the size of the type class. And so we need nh of the type bits per type class to indicate which position in the lexicographic order of all strings with that type a particular string x of 1 through n is. So we need this many additional bits, right? And so therefore we have this upper bound, right? We have this many bits to say, okay, this is the type of the string. Whoops, what's going on here? Yikes. We've got way out of sync. We're way behind now. How did this happen? I know how it happened. I pressed one of these little things. This is not a good way to do this. There we go. Almost there. Okay, so we have this part here, which is the type. This sort of allows us to compute the type, and then this part here chooses which string within that type class it is. And then some constant. And then we take the expected value. We've got the following. Now the last thing we need to do is break apart this entropy here, because this isn't exactly in the form that we want. Right, everything else is. So what we're going to do is, first of all, note that when we say that the number of times in this string the symbol I occurred, let's just call this n of I, and here's just an indicator of what it is. It's just counting over all n, the number of times that xj was equal to I. And so therefore, if we take the expected value of the random variable string, of n of I times the random variable string, we're just going to get p of I times n, where p of I is the probability of the ith symbol. That should be clear. That's one thing we're going to use. And then the second thing we're going to use is the concavity of the entropy. So if we take the expected value of h of some random distribution, because in some sense this is what we're doing here, right? This is the h of a random distribution, because x is a random variable here. Let's just zoom in on this and figure out, make sure that we're clear on what this thing is. All right, let's erase this a little bit. Get some space here. So x is the random variable. This thing here is random, right? And it's the type. It's a random type. Okay. And so h is a random variable. Right, because it's the entropy of a random type, and the random type comes about because it's a random string, it's a random source string. And we're taking, so then the entropy is a random variable, so we're taking the expected entropy, which is now no longer random once we take the expected value. So what we need, and what I said before, is we need to get that back into the form of the original theorem. Let's finish this proof. So we're going to use the concavity of entropy. So here's this expected entropy quantity. And that's written as this way. Here's the actual way that it's written. We take the sum over all strings, the probability of the strings, of the entropy of the type of that string. This is the entropy of the type of the string. Concavity, Jensen's inequality, if you will. So now what we're doing is we're taking the expected distributions. But now we have this property up here, which allows us to say, oh, that is just p of I times n. in each case. Once we do that, we see that that's equal to the entropy of x, because the n's cancel out. So we're done. Okay, so the next topic will be algorithmic randomness. So we're going to define randomness without randomness. We're going to define randomness without probabilities. We're going to define probabilities without randomness. We're going to define nothing without nothing. So come on Monday, tell your friends, tell your family. It should be an interesting lecture. Hopefully I will do justice to the intricacy and sort of fascinating aspects of the topic that we're going to be talking about. So I'll see you all on Monday.